let me share my keynote directly. Does that look all right?
Yeah, that's great.
Okay, so yeah, thank you very much for the invitation, and I want to thank the local host for making the hybrid meeting so seamless. Needless to say, we would have much preferred to visit in person. Today I'm going to be talking about FRB applications, and specifically what you might loosely call FRB baryon cosmology. So if you think of a typical sightline and try to model the FRB DM budget, it might look something like this. Suppose you're at a high latitude, the ISM contributes some fraction of the total DM, the halo a little more, although as folks like Wei Li have pointed out, you really don't know how much the halo contributes. As Vikram mentioned in his previous talk, it's probably a lot less than we've been assuming. Probably less than 30, maybe even less than 10. The lion's share typically comes from the intergalactic medium, or the IGM. So even though the IGM is very diffuse, this is by far the longest path through which the FRB travels. So it ends up dominating the DM in most cases. And then presumably the FRB source resides in some host galaxy, which will have its own ISM, and maybe there's some plasma near the source in a supernova remnant or an H2 region or a magnetar wind or something. But even that is too simplistic, and that's because for an FRB at redshift of about 0.4, you expect to intersect at least one foreground galaxy. That galaxy's halo will be full of gas, and the circumgalactic medium will contribute to the dispersion measure of the FRB. Now, the amount the CGM contributes will depend, of course, on impact parameter, but it'll also depend on the as yet unknown distribution of baryons in that halo. And this is a big and important open question. Along special sightlines, you might intersect or even be embedded in a galaxy cluster, in which case the intercluster medium, or the ICM, will contribute a significant amount of dispersion, particularly if you're well inside the virial radius. But more on that later. So since the field's inception in 2007, it's been a central goal to use a large number of fast radio bursts to try to pin down the so-called missing baryons. So this is the final sentence of Doug's paper from 2007, where they say if redshifts of their host galaxies are measurable, the potential of a population of radio bursts at cosmological distances to probe the ionized IGM is very exciting. And ever since then, there have been these twin efforts going on in parallel where we're trying to answer the question, what are FRBs and how can we use them? So in the latter category, FRBs as a probe, we've already talked about the missing baryons. Gravitational lensing is, of course, very exciting. I believe there are some talks today on that. And then finally, trying to measure the cosmological parameters, including H0. FRBs, the mystery, of course, these topics have been covered this week as well. We want to know the progenitors, the coherent radio emission mechanism, host galaxies, things like offset distributions or specific star formation rates. And then, of course, repetition. Why are some FRBs repeaters, and why are some of those repeaters periodic or at least modulated? Now, I've written these as separate categories, but you should think of them as kind of flowing in and out of each other. For example, if all of the host galaxies of fast radio bursts were like 1905-20, I think this would make finding the missing baryons with FRBs really difficult. Remember, 1905-20 has of order 1,000 units of DM in the host. In the same way, if you want to measure cosmological parameters, my personal opinion is that the best way we'll be able to do that is by pinning down the missing baryons. Go out, try to measure a baryon power spectrum, and then hand it to billion-euro weak lensing experiments like Euclid, one of whose key systematics is the distribution of baryons below 10 megaparsecs. So we all know the McCord relation. JP showed that extragalactic DM increases with the redshift of the FRB, which of course was not guaranteed before we started localizing them. And the slope of this relationship tells you something about omega b. So in some superficial sense, we've already located the missing baryons, but we already knew omega b from the CMB and from Big Bang nucleosynthesis, What we really want is the distribution. We want that distribution because it has wide-ranging impacts on fields from galaxy formation and feedback to cosmology, weak lensing, and KSC. And these baryons are really hard to detect otherwise. They're also hard to simulate. And that has to do with the enormous range of physical scales involved and the complex nonlinear physics involved. So gas from the warm, hot intergalactic medium will fall into gravitational potential wells. It'll cool down radiatively, eventually form stars. And if this were unregulated, then all of the baryons in the universe would form stars. But we know this isn't the case. Star formation is much lower today than it was at redshift 2, where it peaked. And this is because of negative feedback. That's from star formation and AGN and other complex processes that we kind of have to assume the physics of when we're doing these large cosmological simulations. So this topic of feedback is really the bone in the throat of galaxy formation. Just to show you how different the results can be when you use different feedback star formation prescriptions. This is from Stewart et al. 2017. This is the same galaxy, the same initial conditions. And you can see the gas distribution. In this case, it's cold gas. You can see just visually, it's very different because of these subgrid models. I think more relevant to us as FRB astronomers, this is the original Illustris on the left versus Illustris, the next generation, on the right. And even though these two simulations are the same volume and they have the same dark matter distribution, they're almost unrecognizable when you look at the gas distribution. This is another way of seeing that. So here I'm plotting the fraction of mass in halos that are in baryons as a function of the halo mass. And you can see there are these order 1 disagreements between the different cosmological simulations, Simba, Romulus, Bahamas, and Illustris. So the baryons are not just hard to detect, they're also really hard to simulate. What we would like, ideally, is a large population of localized fast radio bursts. The next best thing to a large population of localized FRBs is a large population of unlocalized FRBs. So last year, CHIME published its first FRB catalog, in which there were several hundred FRBs localized to a few arc minutes. And so without arc-second localizations, you can't get a host galaxy, you can't get a redshift, and you cannot associate that sightline with intervening galaxies beyond about 50 megaparsecs away. And so instead, we focused on galaxies in the local universe within about 50 megaparsecs, which I'm showing here, whose halos were intersected by those sightlines. So here I'm showing the FRBs from the first CHIME catalog. The color corresponds to dispersion measure. And then we ask the question, do the FRBs that intersect galaxies within 50 megaparsecs have any excess dispersion measure compared to the sample that doesn't? And so we found the first statistical evidence for halo gas using a sample of fast radio bursts. That's what I'm showing here. On the bottom, I'm showing DM excess between these two samples as a function of threshold impact parameter. And if we convert the simulation comparison that I showed before into DM as a function of halo mass, what we find is that the excess we see cannot really be explained by any of these simulations if it were just the CGM of field galaxies. But it turns out about 3/4 of the galaxies in our sample belong to groups. And the groups will have a shared intergroup medium, and this plasma can account for the DM excess that we saw. Wu and McQuinn did a similar analysis. They took the CHIME catalog and looked for excess DM as a function of impact parameter normalized by virial radius. They used different weighting and a slightly different statistical method, but they found a similar effect, although a little bit more marginal than in our case. So I won't spend much time on FRB gravitational lensing, but there is one kind of fun application of this to CGM studies. So in the past, we've learned a fair bit about the CGM and the IGM on small scales from lensed quasars using absorption spectroscopy. And you can do the same thing with a strongly lensed fast radio burst. If you're lensed by a massive galaxy, then the two lensing images, two or more, will have different impact parameters through the CGM in that lens halo. Now, because the deflection angles are relatively small, the only difference in observed DM between the different lens copies is going to come from the CGM of the lens galaxy, as you can see in this cartoon. So just with a single event, you can actually say something about the differential line of sight density of plasma, because delta DM will just be the difference in DM from that CGM, where theta is going to be the impact parameter times the distance, the angular diameter distance to the lens galaxy. Okay, so Vikram gave a great introduction to the DSA 110 and showed the first 30 localizations. If we go back to the McCord relation, we see that they land on this DM cosmic versus redshift relationship, roughly as you'd expect. The scatter around the mean is going to tell you something about the prevalence of voids and filaments, as well as intervening CGM and the host galaxy distribution and so on. But fundamentally, that's a one-point statistic, and it's sort of messy to deal with. Ideally, we want a two-point statistic. We want to correlate FRB DMs with structure in the foreground. This is part of the program for FlimFlam, who want to map out all of the structure in the foreground of ASCAP FRBs. And I think there's a talk later today, which I think will be very exciting. We want to do something similar with the DSA 110 FRBs. And so I've started with the DESI Legacy Imaging Survey, DR9 catalog here. These are mostly photo-Cs. And what you're seeing is a cone with an opening angle of about 5 arc minutes, and all the galaxies in the vicinity of our fast radio burst, which is plotted with that green star. The orange dots are potential interveners, galaxies that come with roughly a virial radius of our line of sight. And for most FRBs, it's roughly what you'd expect, 0, 1, 2, in some cases a few intervening galaxies. Two sources really stood out. You can see this one here. Before we actually localized it to a host galaxy, we expected it to be at about redshift 0.6 to 0.7. Its extragalactic DM was 575, so we assumed it would be far away. But you can see at redshift 1, there's this big wall of structure where there are a whole bunch of candidate interveners. And sure enough, when we actually localized the FRB and got a host galaxy out of it, the host galaxy was dead in the middle of this overdensity. The same is true for another one, although in this case it's less severe. We expected it to be at about redshift 0.25. Instead, it's at about redshift 0.09 in the middle of another overdensity. And here I'm showing the dynamic spectra. You can see they're actually quite close on the sky, and so they scintillate in similar ways, presumably from the Milky Way. This is another way to view them. These are those light cones, but now I'm showing projected galaxy number density. And sure enough, when I cross-matched these FRB positions against group and cluster catalogs, they both resided in massive galaxy clusters, and actually very well-known galaxy clusters. This is George Abel's thesis from Caltech in 1957. And you can see both FRBs belong to galaxy clusters in this initial Abel cluster catalog. They're actually next to each other in the catalog, and that's because they're separated on sky by just a couple of degrees. The DSA 110 is a transit instrument. For most of 2022, we were parked at 72 degrees declination. The reason this is interesting is not just... Oh, that's too bad, my video won't play. Okay, the reason this is interesting is not just because it's the first time an FRB has been localized to a galaxy cluster, but also because of the impact that we think the ICM, or the intercluster medium, will have on the FRB. So fortunately, both of these clusters had plenty of archival data, including X-ray and SC data. So this is Abel 2310. The offset of this FRB's host galaxy is about 520 kiloparsecs, well within R500 for this cluster. It's at redshift 0.1125. And it's also in the Planck SZ cluster catalog, so it's also got a published SZ detection. The next FRB is in Able 2311. It's a little farther out, a little beyond the virial radius, at about 870 kiloparsecs. In this case, it was actually not in the SZ cluster catalog, although we went back to archival data and made a measurement of the Compton-Y parameter at that position. Vikram already mentioned this, but the host galaxy for this source is very interesting. It's very massive, effectively no star formation, and this appears to be the first ever early type host galaxy for a fast radio burst. So I encourage everybody to keep an eye on both of these papers, one which will describe the impact of the ICM, and Kriti Sharma's paper which will describe the host galaxies. So if you try to model the various components of the DM budget for each source, you end up with a PDF, probability distribution, from the ICM for the first FRB that looks something like this. You can see that the ICM likely dominates the DM budget of this source, which makes sense. I mean, we expected it to be at redshift 0.7, ended up being at redshift 0.1, so the DM likely comes from the ICM. In the case of the FRB, that's at 870 kiloparsecs in projection from the center. It's a little more marginal, but we expect that the ICM likely contributes maybe 50 or 100 or so units to the total DM of the source. So if we go back to some galaxy cluster simulations, or a large cosmological simulation, in this case TNG 300, and we just pull out galaxy clusters whose masses are similar to the ones we've observed, we can ask, do the DMs we see correspond to the DMs you expect in this simulation? So that's what I'm showing here. On the bottom panel, you see DM curves. DM is a function of impact parameter, assuming the host galaxy is roughly halfway through the cluster. And you see there's a fair bit of variation between the halos and even within a halo at different position angles, but the measurements roughly agree with the simulations. So what we have is this new probe of the ICM with fast radio bursts. The SZ effect measures an integral of electron density weighted by temperature. X-ray luminosity goes like the integral of NE squared. Of course, DM is just the integral of NE. And Faraday rotation measure is NE weighted by line of sight magnetic field strength. Now, it'll be very hard to compete with X-ray emission to pin down NE well within the virial radius, but because it's so strongly dependent on the density, you lose sensitivity beyond about R500 or R200 using X-ray observations. And therefore, FRBs could play a really useful role in measuring this gas in the outskirts of the intercluster medium and where the ICM becomes the warm-hot intergalactic medium. FRBs are also, of course, the only source, extragalactic source, for which we can measure both RM and dispersion measure. And so if we can attribute some portion of the RM and the DM to the intercluster medium, then we can say something about the mean magnetic field strength. So if we do that with one of our fast radio bursts, whose RM is of order 100, we get a mean magnetic field strength of a few microgauss, in line with expectations. Another fun thing you can do is divide the Compton-Y parameter by dispersion measure. And this gives you a proxy for the line of sight average temperature of the gas. When we do this in the case of the FRB, that's 500 kiloparsecs from the center of the cluster. We find that the gas is a few keV. Again, this does not revolutionize the field of studying the intercluster medium, but this is, I think, the first time we've ever measured a gas temperature using FRB dispersion measures. Okay, so we're very fortunate at Caltech to have quite a bit of optical IR resources. And so we've been awarded 5 nights in the next several months with Keck using DAMOS to map out the fields of our fast radio bursts. 4 nights with Palomar. Actually, I found out 2 hours ago that I'll be observing with Palomar tonight, which is unfortunate because I'll have to leave the meeting and start the observing, but it's good because I'll be awake for the rest of the meeting. Anyway, we think we can map out the fields of 30 of our FRBs, getting roughly 200 galaxy spectra for each of those fields. And with this, we hope to do some of these CGM studies and baryon mapping applications that I've been describing. Okay, so Vikram already introduced the DSA 2000.
5 minutes
I think the good
left.
news is, thank you. The good news is that for surveys like DSA 2000 and CHORD, we don't seem to be running out of sources at low brightnesses. There's plenty of action in the millisecond Milojansky radio sky, evidenced by the implied rate from FAST. So we were talking about source counts below Jansky, I think on the first day. And so this is my attempt at a sort of back of the envelope estimate of source counts over almost 4 orders of magnitude. I think you don't quite get Euclidean source counts all the way down, but you don't flatten out very quickly. There's something like 100,000 FRBs across the sky above the sensitivity of FAST, and DSA 2000 is only a couple of times less sensitive than FAST, but with 500 times the field of view, so you can imagine it should find a large number of sources. Maybe as many as 10,000 FRBs per year localized to arcsecond precision and below. Another nice thing about having all this sensitivity is that it seems likely that there's an anti-correlation between brightness and distance. And so by going down to 20 or so Milojansky milliseconds, we'll likely be probing a very deep redshift distribution of FRBs. Now, what would we do with this population? Well, I think one thing we would do is try to pin down the baryon power spectrum. So here I'm just showing, again, significant disagreement between simulations on the effect of baryons on the power spectrum. What I'm plotting on the y-axis is the dark matter plus baryons power spectrum divided by dark matter only. So you get order 1 deviations from dark matter only, and also order 1 disagreement between the different simulation codes. And so really, what we want to do is come in and say, here's what we think the distribution of baryons is, and this will alleviate one of the main systematics for upcoming precision cosmology experiments. Another fun thing that DSA 2000 will do that I think is probably unique to that survey, at least in terms of FRB surveys, is it'll spend 5% of its time on a deep drilling field. So this will be just 10 square degrees, where it could find as many as 500 FRBs per year. So you end up with this really dense distribution of fast radio bursts, where just about every cluster in this volume out to maybe redshift 2 will be intersected by at least 1 FRB. You'll also have all the data from XMM and LST, Chandra, and the Cosmos field. So you have this really well mapped out volume of the universe with which you can do both FRB applications and study their evolution over time. CHORD is another telescope that's expected to find and localize a large number of fast radio bursts. Now, looking at the future, how would we design a megasource survey? How would we find 1 million FRBs? And a follow-up question, do we actually need 1 million FRBs? Well, I think it depends on what your science is. If your science is trying to understand what they are and studying progenitors, then 1 million FRBs is probably overkill. I don't think you'll learn that much more with 1 million than you will with, say, 50,000. If you're doing cosmology or gravitational lensing, you absolutely want 1 million FRBs. So how would you do that? Well, I think the first thing you do is you do away with dishes. And basically, you follow in the path of burst. So you end up with a dense aperture array. I call these sorts of systems coherent all-sky monitors, or CASMs. We can see if that name actually sticks. Vikram just mentioned the design here at Caltech. It's called TRACK. One of the differences with burst being that we'll probably have a pseudo-random distribution of antennas. We won't be FFT beamforming, we'll be brute force beamforming. And just to conclude, I've tried to focus today on the applications within FRB cosmology where fast radio bursts are really uniquely suited. In particular, finding this diffuse ionized gas that are otherwise so difficult to track down. So with that, I'll say thank you to my hosts, and I'll happily take questions.
Thank you, Jan. Now, questions, comments, please. Okay, let's go to online question first, then when.
Online question from Susumu. Yeah, thank you for the great results. So for the FRB in the cluster, what are their properties in terms of scattering? And can you try to say something about turbulence in the ICM?
Yeah, this has been kind of a head scratcher. So we find no evidence of scattering in this one. For this fast radio burst, which is at about 870 kiloparsecs from the center, we find about 80 microseconds of scattering, and this is really weird because it resides in an elliptical galaxy, right? So we don't expect this host galaxy to have much ISM. If it's in a globular cluster of that host galaxy, we also don't expect there to be a lot of local plasma. We've constrained the distance of the first screen, the screen closest to the source, to be about 150 or 200 kiloparsecs. So maybe it's in some outflow, or maybe turbulence in the ICM, I really don't know.
Okay, very interesting, thank you.
Okay, Willie.
Hi, yeah, Willie. Thanks for the talk. Obviously, the baryons are a killer application for FRBs. Learn so much more. I don't know if you've thought about the Veddetem and Finney arguments that CGM, that due to the measured absorption systems in the optical, they interpret it's almost inevitable that you get huge amounts of plasma lensing from cold clouds that are thought to exist due to optical measurements. And yet you don't seem to report any in this new sample either. Is that becoming an issue? Like, did somebody get something totally wrong, or is it a big tension now that that still is going to go and retract this paper?
I think I agree with your impression that this just hasn't really been seen, and also the fact that when we do see FRBs that are temporally scattered, they're often also scintillating, which you wouldn't expect if the scattering stream were halfway between us and the source in a cold cloudlet of an intervening CGM, for example. So yeah, I kind of agree. I don't think it's been seen, and it's clearly not that common. Although, who knows?
Okay. Your question?
Great talk, yeah. I wonder, you show intervening galaxies, and I wonder how complete the galaxy catalog is if you, for example, show up to redshift of 0.7 or so. So I wonder, what is your thought and future plan?
Yeah, so I guess the answer is not especially complete, and also most of these are photo-Zs, so we don't have a good sense of what their actual redshifts are. Yeah, this is kind of why we're doing these deeper images with Deimos on Keck to get a more complete sample, especially the large halos in front of our FRBs.
Okay, thanks.
Okay, any short question? Okay, this one.
Oh, very nice talk. So you found two host galaxies in galaxy cluster environment, but how about other FRB host galaxies? Did you find FRBs in less density environment, for example?
In what kind of environments?
Sorry. You found FRB host galaxies in galaxy clusters environment. I'm asking if you also found other FRB host galaxies in low number density environment, for example, void region or in the cosmic galaxy structures.
Yeah, so Vicar mentioned that there have been 21 localizations, I guess, before the DSA, and now there's 30. These are the only two galaxies I'm aware of, host galaxies that belong to galaxy clusters. So clearly it's not that common, though maybe it's more common than you would have thought a priori. I guess TBD if any of these reside in large voids. This is kind of the purpose of our structure mapping program with Keck and Palomar.
Okay, thank you very much.
Okay, thank you very much. Time is up, so let's thank Liam again.